Okay, we're going to talk about volume by revolution and two different methods for finding volume of three-dimensional figures. So I'm going to show you some pictures first to kind of help you understand what's going on here. So we are going to take a two-dimensional figure like this triangle, and what we're going to do is we're going to rotate it to create a three-dimensional figure. So in this particular question, we would be rotating this triangle about the y-axis. So that would make it spin around kind of from side to side like you would spin a top to create the shape of a cone. Okay, here's another moving example of what rotating a function about an axis could look like. So in this particular demonstration, you have kind of this roller coaster looking graph. If you rotate it about the x-axis, you would end up with a three-dimensional shape that kind of looks like a vase. All right, so now what we want to try to do is we want to try to figure out ways to find the volume of these three-dimensional shapes. And one technique to do that is called the disk method. And so in the disk method, what you're doing is you're taking your three-dimensional shape and you're kind of turning it into slices. And those slices are going to be round discs, okay? Because your shape has been created by going around in a circle, so the shape itself is round. And if you were to like slice this thing up like you slice a piece of bread, every slice would have a round shape to it. Different sizes, but a round shape. So we are going to slice it into thin discs, and then we're going to find the area of each disc, and then use that to help us find volume, because the volume could be computed by adding all the areas of these discs to fill up that 3D space. So let me give you an example of what that might look like. So this is actually example number 2 in your notes. It says set up and evaluate each integral that gives the volume of the solid by revolving the region around the x-axis. So I need to draw this function first, which this is 1 minus x. So I have it starting at 1 on the x-axis and would be going down 1 over 1. So here's where it would be ending, and that is a straight line. And I'm not going to even try to do it with my airliner. So there you go. Now, to make the drawing pretty, I'm going to show you how to make this into a kind of three-dimensional looking figure. So this would suffice as far as just like the two-dimensional shape. But we are rotating this thing about the x-axis. So we want to make it look like it's been rotated this way, okay, around the x-axis. So I am going to reflect this image over the x-axis. And I better extend the y-axis down so I can see that too. Okay, so there is our image reflected. And then we are going to draw like a section of its three-dimensional shape by drawing a little disc. Okay, so we're going to do a little line here. Really, you could do this anywhere. Little line here that kind of goes through. And then you're going to kind of curve it so it makes like a semicircle. Oh my gosh, this looks so bad on the airliner. I'll have to show you this in class because I can do it a lot better. And then make kind of a dotted line going backwards. So this is supposed to be like a wedge. It's supposed to be a little semicircle here. So this would be kind of the center of our disc. And this right here would be the radius. Let me do that in a different color so it stands out a little better. Okay, so imagine that we have an infinite number of these little discs created from this three-dimensional figure that we just made. And I want to find the area of each of those little discs. So let's start with the fact that area of, this is area of a circle really, area of a circle is pi times radius squared. Okay, now I would like for you to give me a different way of identifying the radius because the radius is going to change based on where it's at on this function, right? Well, if you look at the way the radius is drawn, it's drawn from the x-axis up to the line. And that means that this y value, whatever this y value is on this line, is going to be also equal to the radius value. So we're going to say that the radius is equal to the y value. Okay, so we're going to call this pi times y squared. And then basically this is how we would find the area of each of our little discs. And to find volume, we would have to multiply by the width, right? So I'm going to take the area of each little disc, which we said would be pi times y squared, and multiply by the width of each disc. The width is actually going to be dx, because dx represents the change in x values, and that's exactly what we're dealing with here, is the change in x values will determine how wide each of these little discs would be. Then we want to have our integral, and we want it to go on this one from 0 to 1, because the x values only go from 0 to 1. Now, the way this is set up is okay for now. However, we have a situation like before where these two variables don't agree, because we have y's and then here we have x's. So we are going to switch it, and we're going to find something to substitute in place of y. Well, right here, it says the y is equal to negative x plus 1. And I really would rather have that look like 1 minus x. So I'm going to change it. And so we're just going to substitute 1 minus x in place of y. All right, now we are ready to integrate. But before we can do that, we're going to have to kind of use some algebra to simplify this. So we're going to make it, instead of 1 minus x quantity squared, we're going to actually square this. So it'd be 1 minus 2x plus x squared dx. And actually, I think I'm just going to go ahead and move pi to the outside because it's a constant value. Okay, now I can integrate. So now we can say, let's see, pi will stay on the outside. The antiderivative of 1 is x. And then we would have 2 over 2 x squared plus 1/3 x to the third, evaluated from 0 to 1. I feel like from here you guys are probably just fine with evaluating your integrals. So feel free to fast forward if you would like. So answer for this one is looking like pi times 1/3, so pi by 3. So volume of this 3D shape would be pi by 3. All right, let's skip and find another one where we are making a disk. But let's go to example 4 because it's going to be a little different. So it says revolve the function y equals x squared about the y-axis. So that would be a parabola. Oh my gosh. This is just beautiful, isn't it? You know what? Why did I not think of this? I'm going to cheat. Watch this. Let's clone it and flip it. There we go. I like it. Much better. Okay, so there's my function y equals x squared. We are rotating it around the y-axis, so like kind of around this way, okay? Around this way. So let's draw a disk. And it's gonna be flipped on its side this time because we're rotating our graph around the y-axis this time. So I'm making a little disc. That wasn't too bad. And then the radius of the disc would be like from the center all the way to here. That's the radius. Okay, so let's go to finding the area of the disk first. So area is pi times radius squared, but we want to identify the radius differently. So in this case, the radius goes from side to side instead of from bottom to top. So that means that the radius is equal to the x value on the curve. So I'm just going to call it the x value for right now. So pi x squared. And then remember the width of each of your little sections or wedges is just called dx or dy. Now in this case, the width is vertical. So it's going to be called dy because it's equal to the change in the y values since this is going up and down. So what's our volume integral going to look like? We're going to have our area, which is pi x squared. We're going to have dy. And we're going to have our, it's evaluated from 0 to 4. Because it said go from 0 to 4. Again, we're going to have to figure out how to fix this because we have to have variables that agree. So like if this is dy, then this has to be in terms of y. It's going to work out pretty nicely because right up here it says that x squared is equal to y. So I can take out the x squared and put a y in its place. From here, I feel like you're pretty good with integrating and such right by now. So we are just doing our normal integration stuff. So 1/2 y squared, plug in 4, plug in 0, and you're done. So it's looking like 8 is going to be our answer. You know what? There was a pi in here. I totally forgot it. I know what you're thinking. You're thinking, it wouldn't be a normal BC lesson if Mrs. Strope didn't forget a number at some point. So you're welcome. I did that just for you. Got to keep things interesting, right? Anyway, let's do one more. You know what? No, we're just going to keep going. Okay, so I can always do more examples in class if you're not sure of the disk method. But let's go to the washer method for this lesson. This is the last part. So what will happen sometimes is the way that your functions are drawn, if there is a gap between your equation and the x-axis or the y-axis, and then you rotate that equation to make a three-dimensional figure, there's going to be a gap in the middle of your equation or your 3D figure. So you would have something that resembles a washer, which is like a donut, okay? So if you look at this little demonstration here, it's showing you, here's a parabola, a half of a parabola, but I'm going to rotate it about the x-axis. Well, there's going to be a gap because it doesn't touch the x-axis everywhere. So in this case, we're going to have to do something called the washer method or the donut method, if you'd rather call it that, to find the total volume. So it's still this idea of taking a 3D shape and slicing it and looking at little slices, one piece at a time. But our slices are no longer discs. Our slices are now donuts, okay? So here's another example of something that would create like a donut shape. You see how there's a gap between g of x and the x-axis? This is going to make a donut because it's got a gap here, so it would make a hole in the middle.